Hello. In the last video we looked to see how electrons filled the energy levels that are available to them. And they always start, according to the Aufbau principle, at the lowest energy level first. But now we want to look at the wave function for, let's say, the 1s orbital. That is the lowest energy level for the electrons. And we find that if we plot the wave function squared, which of course is the probability of finding the electron, according to the distance from the nucleus, we find that it looks something like this, where the peak is at what's called Bohr radius. And the Bohr radius is essentially 0.5 times 10 to the minus 10 angstroms. So you're most likely to find the electron 0.5 times 10 to the minus 10, meters. It's 0.5 angstroms, which is 0.5 times 10 to the minus 10 meters. So you're most likely to find the electron about half an angstrom from the nucleus. But it could be anywhere under this curve. If we now look at the probability distribution for the 2s level, and here is psi squared, then the probability distribution squared looks something like this, where the maximum, or the most likely place to find, is 3 Bohr radii, which would be about 1.5 angstroms. But you could find the electron here, very close to the nucleus. You're more likely to find the electron here. But you will never find the electron there because the probability is exactly 0. And here is one of those fascinating quantum mechanical effects, that the electron could sometimes be here and sometimes here, but it can never be here, not even in passing. And so you've got the fascinating thing that an electron can get from, say, 3 angstroms to maybe half an angstrom away from the nucleus without ever having gone through that point. It just dematerializes in one place and materializes somewhere else. Now let's look and see how chemistry happens. Let's take two elements. One is sodium, we've already looked at that. That is an element that has the first two energy levels completely full and has one electron in the 3s orbital. And we're also going to consider chlorine, which sits here. That means that it's in the 3p level and it has 5 electrons in a level which would normally take 6. So it's essentially 1 electron short of being a complete shell. This means that you can represent sodium as having the first 2 levels completely full and just 1 electron in the 3s level. Chlorine, that's sodium. Chlorine, by contrast, has the first 2 levels full and the third 3s level full and the 3p level almost full. It just has space for 1 more electron. And that means that there's the capability for sodium to lend chlorine its extra electron, because then sodium will be complete and chlorine will be complete. And that's exactly what happens. Sodium, which has a spare electron, lends it to chlorine, and that forms a bond. And when it does so, sodium will be slightly positively charged because it's lost an electron, and chlorine will be slightly negatively charged because it's gained an electron. And that's sodium and chlorine bonding together to form sodium chloride. And here's the fascinating thing. Sodium and chlorine are both extremely poisonous, toxic and highly reactive elements. You wouldn't want to eat either of them because they'd make you very ill. But when they join together, they form a substance known as common salt, and you're perfectly happy to put that on your fish and chips. Now let's look and see what happens when 2 hydrogen atoms come close to one another. Hydrogen, as you know, only has 1 electron, and that sits in the lowest energy level, the 1s level. And so here are 2 hydrogen atoms, each with one electron in the 1s level, and they come together. But what happens when they come together? Pauli's exclusion principle kicks in and says, no, that cannot be, because these two electrons have exactly the same 4 quantum numbers, and that's not allowed. And so when you bring these two atoms together, their energy states have to adjust marginally, so that one is a tiny bit different from the other. And the lower one is given the name bonding, and it's represented by a sigma. And the higher one is represented by sigma star, and that's called antibonding. And what happens is these two electrons come and occupy these levels, but what do? They always want to occupy the lowest energy level. So the electrons will arrange themselves so that one is spin down and one is spin up. And that means that the bonding level is now full, and the antibonding level, marginally above, is empty. And you now have a situation where these two electrons are at a tiny bit lower energy level than they were when they were in separate atoms. And that's the reason that atoms of hydrogen like to form together to form molecules of hydrogen. Each molecule has 2 atoms, because then the 2 electrons can occupy a slightly lower energy level. I now want to look at copper, which sits here in the periodic table. It's in the n equals 4 level, and on the face of it you might think that it had 2 s-level electrons and 9 out of the 10 3d, because this is the 3d level. You remember I told you that 3d actually comes above the 4s level. That's why it comes after it in the periodic table. This is the 3d line of the periodic table. And copper sits here. There are 10 elements in the 3d line, because there were 5 levels, remember, 5 different levels, each with 2 electrons. And you might think that copper has 2 s electrons here and 9 d electrons here. Actually, that's not true. What happens is that all 10 of these levels are full, but only 1 of the s levels is full. So copper actually has 1 electron in the 4s level, and all the 3d levels are full. So now let's consider 1 mole of copper. A mole is you simply take the atomic number of the element, in copper's case that's 29, and you weigh out 29 grams of copper, and that's known as 1 mole. And Avogadro said that if you have a mole of a substance, then it will contain 6 times 10 to the 23 atoms per mole. So if you have 29 grams of copper, which would be a few cc's, a few cubic centimetres, that will contain 6 times 10 to the 23 atoms. And they all have electrons, 1 electron in the 4s level. So you will have 6 times 10 to the 23, and I can't possibly draw them all, levels, 1 for each atom, and in each case they will have 1 4s electron sitting in them. And you're bringing them all together because they are in 1 mole of copper, a few cc's. And Pauli's exclusion principle kicks in again and says, no, you can't do that. If you did that, they would all have the same 4 quantum numbers, and that's not allowed. And so, rather like hydrogen, all of those energy levels have got to adjust, so they're all just a tiny bit different. But unlike hydrogen, where it was only 2, we now have 6 times 10 to the 23 levels that have all got to be slightly different. And so you end up with energy levels that are infinitesimally separated from the one above. And there are 6 times 10 to the 23 of those levels, and they all occupy an energy distance of about 5 eV. So you can do the maths. You'll find that the separation between any two levels is very, very small indeed. Now let's just remind ourselves we had 6 times 10 to the 23 atoms, and each one had 1 electron in an orbital that could accommodate 2. What happens when all those orbitals separate out? Well, the electrons will fill them in the same way as they did with hydrogen. They start with the bottom one first, and they fill it. 1 up, 1 down. And then the next one, 1 up, 1 down. And then the next one, 1 up, 1 down. And so they'll continue to do that until half of those orbitals are completely full. And the other half will be empty. This then becomes the bonding set of orbitals, and these are the anti-bonding orbitals. And they now take on a new name. The bonding orbitals become known as the valence band, and the anti-bonding orbitals become known as the conducting band. Now we can represent these two bands. They're called bands because the levels are so close together they pretty much form a band. We can represent this like this, that here are the bands. One half is completely full of electrons and the other half is empty. That's the valence band, that's the conducting band. But they actually touch one another. There is no separation between these. And you'll see that therefore an electron that happens to be in an energy level, because these are all in their ground state, if it receives a little bit of energy from a photon, can easily be promoted into the conduction band. Even at room temperature, the room temperature is equivalent to 1/40th of an electron volt. The photons, the infrared photons at room temperature, have an energy of 1/40th of an electron volt, and that's easily enough to kick loads of electrons up into the conduction band. And what happens then? If you were to get a battery and apply a potential difference across that, all those electrons are free and mobile and can flow. And that's what makes copper such a good conductor, because the electrons can be promoted easily, even at room temperature. Millions of them can be promoted in order to be free to flow along this conduction band. By contrast, an insulator like diamond, for example, looks like this. Here is the valence band, which is full. Here is the conduction band, which is empty. But in the case of an insulator, there's a gap of as much as 5 electron volts between the two. And now you can see that if you've got photons with energy of 1/40th of an electron volt, they've got no chance of promoting electrons here into the conducting band. So the conducting band will be pretty much empty. There will of course be a few electrons in it, but nowhere near as much as for copper. And that's why if you put a potential difference across the conducting band now, there just aren't any electrons to flow, and so no current flows, and that's why it's an insulator. You can't get a current to flow across an insulator. Now in the next video we'll be looking at a very special material called a semiconductor.